Piece of shit.
Hey, man, what's going on? What is that thing? That looks awesome.
Come on.
What is it? I've never seen it.
I've made a gravitational wave machine. It's not friggin' working.
Are those car batteries?
They are car batteries, and I've hooked it up in accordance with Einsteinian general relativity. It's just not working. I don't understand why you are not working.
What's it supposed to do? Why?
It's meant to bend space-time, so...
But I'm not feeling anything, and it's not changing anything around me.
How would we know if it was working anyway? Like, I don't know.
Shouldn't we feel as if space-time's stretching? It's just such
I don't
a
know.
piece of
Maybe
shit.
we should ask someone who knows shit about this.
Yeah, let me just go throw it in the bin. Okay, let's get to it.
How hard this was to research and try and sound genuinely like I was doing work.
Our next guest is our favourite astrophysicist. If he's not writing books or articles on his blog, he's researching black holes and dark matter. However, today he's making a very poor professional decision by wasting his time talking to idiots like us. Please welcome our good friend, Professor Geraint Lewis. Thank you, Professor.
Hi, how's it going?
This is the treble.
I know,
This is the treble.
Yeah. A record.
Yeah, that's right. I thought you would have learned the second time. Man. It's your own fault for coming back this time.
Yeah, it's your fault now. So you've been doing a bit of travelling with your book, A Fortunate Universe.
Yes. I got back recently from the UK. I did a 10-day kind of book tour, went right around the country, spoke in Cambridge and Armagh in Ireland. I'd never been to Ireland before. It was really nice. And Durham and Oxford and at the Royal Institution in London.
Wait, you've never been to Ireland? You're Welsh. That's crazy.
That's right. I'd never been to Ireland.
I don't know. Usually you just assume
come on,
someone
mate.
lives in the area, they might go to Ireland.
Have you been to Tasmania?
No.
Yeah, there is actually an ocean between Wales and Ireland. So.
I know.
Yeah.
I know. Okay. I don't think I want him on a fourth time. So you were saying that you got to kind of see some amazing things when you were over there. You told us before.
Well, one of the cool things is that in the basement of the Royal Institution is Faraday's laboratory. It's his actual equipment that, he did all the classic experiments of electromagnetism, etc. So you're sitting there looking at the first electric motor, effectively, right? This is the kind of stuff you got there, and electromagnets, before anybody ever had electromagnets. It is just really cool to think that Faraday was working there. It's really, really cool.
It must have been special to do a lecture there as well.
Lectured in the room that Faraday lectured at the desk where Faraday lectured.
Oh my god, that'd be awesome!
It was very good, and yeah, the vibe. If you ever see any of the Christmas lectures from the Royal Institution, really, really good vibe there. Very, very good crowd of people, etc.
Oh wow! Well,
Wade's about to go to Europe, so he's hitting you up for some information. I think,
Go there. Definitely.
I'll try. Can I do a lecture here? No, you're an idiot. We got you on today because we wanted to discuss with you gravitational waves, because there's been a lot of hype in the media at the moment, and there has been in the past. I think I was looking back at the history of it, even as back as the 70s, they were talking about maybe detecting gravitational waves and all that type of stuff. But recently it's come out that they've detected gravitational waves. There's a lot of people going, what the hell are gravitational waves? What are they?
Okay, so can we go back to the beginning a little bit, right?
Absolutely.
So we need to go back to 1915. We need to go back to Einstein working on his general theory of relativity, which is now how we describe gravity in the universe, okay? And one of the things he did is he changed the way we understand space and time. So instead of them being two separate concepts, as they were in the physics of Newton, united together to give you this thing called space-time. Okay, so it's like the fabric of the universe is the phrase that people use to describe what this thing is that tells us how gravity works. So one of the questions you can ask yourself is, what would happen if I put a pinch into space-time? So I take a piece of space-time and I pinch it and I let go. Now, we can solve the equations, and when you let go, it could just stay as it is, or it could just gently go back to being flat and boring. But what you find is that the properties of space-time are elasticy, in that if you pinch it and you let go, it actually sets up a bit of a vibration, and that vibration in space-time carries. That's the wave aspect. Okay? So this was essentially predicted by Einstein. He realized that if you could put ripples into space-time, they would travel like waves on a pond. So he thought that if you have a big gravitational disturbance, something strange going on with very strong gravity at play, then that could set these waves trickling through the universe, and you should be able to detect them somewhere. So this turned out to be like the last great prediction of Einstein's general theory of relativity. All of the other predictions were tested through the 20s, 30s, 40s, 50s, 60s, etc. And we still had this question about gravitational waves.
Okay.
And the big problem is that while gravity is one of the forces that dominate our everyday life, gravity is a really weak force. So these ripples in space-time, they have a gravitational effect when they get somewhere, but that effect is tiny. So you need to develop equipment sensitive enough to detect the ripples in space-time. And so that people started working on this in the 60s, and there was a famous set of experiments that were done by a guy called Weber, where he was trying to design these first generation of gravitational wave detectors, and he thought he had detected something or not. It's that kind of detection where the scientific phrase is battling down in the noise. Right? Anything can set up a vibration. How do you know if that vibration is a gravitational wave or you bumped your equipment kind of thing? So it's always battling those kind of vibrations. So
yeah, because in early 2004, Bicep thought they had detected primordial gravitational waves, and Bicep's is in the South Pole, and I'm guessing that they're looking at the microwave background radiation and trying to analyze that to detect gravitational waves.
Yes, a little bit more recently, wasn't it 2012 or 14?
I'll go with your figures,
Yeah.
Grant,
No,
over
what did I
Wade's.
say?
I don't care. I'm going
Said 2014. 2014, yeah.
Anyway, yes.
You're probably wrong, Wade, if we're honest. Yeah, okay.
Oh, I agree with that.
So Bicep was looking at, as you said, this cosmic microwave background radiation, and that's the radiation left over from the Big Bang. So they weren't searching to detect gravitational waves directly. They were looking for the impact of gravitational waves on the early universe. So gravitational waves trundling through the early universe would have left an imprint on the cosmic microwave background. And if you can find that imprint, then you can say, yes, those waves existed back then. And there are plenty of our sort of cosmological theories that predict these waves in the early universe. What actually happened is that Bicep 2 had detected a signal, but they hadn't taken into account other potential sources of that signal. They had made a bit of a guess about the influence of dust in our galaxy, dust and dirt, which is this leftover stuff from the evolution of stars. Our galaxy is littered with dust, and that can spoof a gravitational wave signal in the same wavelengths where we see the cosmic microwave background.
Okay.
So when they went back and they had the proper calibration, the potential gravitational wave signature basically died away. So they were fooled by not calibrating their experiment, which is always the killer in science, is your calibration.
Reminds me of the pigeon poo when they were detecting the microwave background radiation back in the day.
Yes. But they at least they thought, that could be an issue, and so they removed the pigeon poo and they removed the pigeons. I think they had them shot through the air. So I don't think they just asked them to leave.
Wasn't there one where they opened the microwave too quickly? Where was that?
There was fast radio bursts, pyritons or something. Yeah. So these things happen. Is that you find there's. Would you like me to digress slightly? One of my favourites.
Absolutely.
One of my favourites, and this might almost be an apocryphal story now, but there was a thing called sodium stars or sodium flare stars. And the people would be observing these particular stars, and as they were observing them, the spectral lines from sodium would appear and disappear very, very quickly. And people couldn't figure out what was going on. What's going on in these stars that sodium lines appear and disappear? And eventually they found out that what was happening is that somebody was going outside the telescope and having a ciggy and sparking the match, which produces a sodium light, and then blowing it out again. So
That's incredible.
Yeah, but these you always, if you find something weird, you've always got to track down the fact that have I been fooled?
Yeah.
Right. So this is like the pigeon poo, and it's what Bicep should have done in the first place before their big result. But
just goes to show how sensitive the equipment is that it can pick up like a sparking match or a microwave being opened too quickly or anything like that.
Absolutely,
it's so sensitive.
Which kind of brings me to my next question. So LIGO has detected the gravitational waves.
Yes.
One of the places that have detected the gravitational waves.
Yeah. So it should explain quite what LIGO
Yes,
is, right?
please.
So it's the laser interferometry Electric Gravitational Observatory, something like that. Yeah.
Going to take your word for it? Yes.
Yeah. So it's actually two detectors separated by a few thousand kilometers in the US. So there's one in Washington in the northwest and one in Louisiana in the south. And so they're identical sort of telescopes, but they don't look like telescopes, right? So what you've got in each of them, you have metal tubes about 3 kilometers long at 90 degrees to one another. They evacuate all the air out of the tubes, and they basically bounce laser light back and forth down those tubes. Okay, so this is your gravitational wave detector. So what do they actually do? In bouncing that laser light back and forth, they're accurately measuring the length of those tubes. Okay, now so you have these tubes, they're 3 kilometers long, and they know that the length to an amazing accuracy. And what happens is, as a gravitational wave comes through, it's a gravitational effect, so gravity squeezes and stretches. And the way a gravitational wave works is that as it travels through, one of the arms gets squeezed and so gets shorter, and the other arm gets stretched and so gets longer. But then as the wave travels through, it reverses. The one that was stretched gets squeezed, and the one that was squeezed gets stretched. So you can imagine that the lengths of the arms are oscillating slightly, but out of phase with each other. Okay? Now, what they're doing, of course, is accurately measuring the length of the tubes. And what they do is they can detect the change in the length of the tube as the gravitational wave comes through. Now, the number that is particularly freaky is that the distance by which the length of the tubes change is around the 1,000th of the width of a proton.
Whoa, so that is very small.
That's tiny.
That is tiny.
Yeah.
But this is why it's taken 100 years to get to the point where we can detect these things. We always knew, I mean, LIGO as an idea has been around for a while, and there have been previous generations. It's all been about sensitivity and pushing down the noise. And so designing special mirrors, which Australia played a part in the design of the mirrors, etc., the CSIRO group.
Woo, represent!
Yes. So, at that kind of accuracy, you have to worry about how much the laser light pushes the mirror, right? Because light carries a push on it, and you have to worry about that push. So, so they get down to that kind of sensitivity whereby they can measure these tiny changes.
Yeah, and so I guess in doing anything like that, you'd have to rule out kind of geological kind of disturbances, some dude leaning against it, having a cigarette or something like that. Like, it would be incredible. Are they pointed exactly the same way, or are they pointed different ways?
They're definitely tilted at different directions because they're on different parts of the Earth's surface. Exactly what their orientations are, I'm not 100% sure. But the key thing is, the reason you have two is that a gravitational wave signature will be detected in both, right? Gravitational waves tend a big wave front, so they travel across the entire surface of the Earth. And so if you get vibrations in one detector, you'll get vibrations in the other. So this is why they have the two, is that exactly that a truck 50 miles away might put a vibration in there, but only in one of them, not the other.
Okay.
So the key thing is, what they want to do is they look for the signature that appears in both.
And how do they locate? Because I noticed that when they came out, they said, it's two stars colliding and, so many million light years away. How do they pinpoint that location if there's a wave traveling through?
It's very hard work, right? So the only thing you can really do is look at the difference in time that the wave arrives at each of the detector. Now, the wave travels at the speed of light. And so basically by saying it arrived in this one a fraction of a second before that one, it came from that direction. Okay. Now, the big problem that you have is that that's a very insensitive kind of direction finder. So if you want to point a telescope in that direction, you want to find things much more accurately on the sky, which is why things have changed recently, because a European gravitational wave detector has now come online, which is called eVirgo, or just Virgo. I'm trying to remember the name. So now you have 3 detectors, and you triangulate even better, which is why there's been this big hoo-ha recently about all the telescopes that were able to do follow-up, because you could start to really find out where things are happening on the sky. There was a lot of excitement recently with the last gravitational wave event, because there were this follow-up, the telescopes from radio to X-ray and gamma ray also saw a flash in the place where the gravitational waves came from. So this wasn't two black holes merging because there's no light signature. So it's thought that these were two neutron stars. So these are these tiny 15-kilometer sort of stars, but with the mass of the sun.
They're essentially giant atoms, aren't they? That's how
Essentially
I've
giant
been
atoms, yeah,
explained to
balls of neutrons mashed together. So people have thought about these collisions for a long, long time, and the fact that we see the gravitational wave signature matches again what we expect. But what happens is instead of two black holes merging and produce a bigger black hole, two neutron stars merge, but they essentially then rip themselves apart. But in that ripping themselves apart, you smash atomic material together, and you create heavy elements. And now some people have suggested that that in this collision, the numbers aren't certain, but maybe 100 times the mass of the Earth was created in gold.
Oh, okay,
right?
wow.
Whoa.
Yeah. So it's only in these violent collisions at supernova, but also now we know that neutron stars merge. That this is where heavy elements like gold are formed. So it's quite spectacular. It's not just gold, of course, but think of all of the heavy metals. They're also produced in this sort of violent merger event, which is pretty cool. Because I said you look at the gold in a piece of gold ring on your finger, and that was made in some of the most violent events in the universe.
Yeah, we're tight asses. Ours are titanium.
Where's titanium formed?
Wherever it is, it's cheaper to get.
Yeah.
And so,
I think we need to let Rio Tinto and BHP know about this, and then they'll join the space race.
Yes.
that's true. That's true. But one of the interesting things is with neutron stars, it's kind of like atoms that have been the electrons have been pushed into the nucleus, isn't it?
That's right. Yes.
And that's this intense gravity that would cause that.
Absolutely. Yes. Yeah. So you create neutron stars in supernova. So you need an immense crushing force, and that happens when you have a big star. The nuclear fuel goes out, and that removes the outward push from all the heat radiating outwards. So the star collapses. So the outer layers collapse on the inner and crush it up to immensely high density, such that the electrons get squeezed into the nucleus, and they merge with the protons to form neutrons. Yeah. And then all of those nuclei are so close together that they pack really, really densely, which is why you can pack the mass of a star into an area not much, about the size of Sydney.
Wow, okay. And can they only get to a certain size, neutron stars?
Well, eventually, if you pack in too much mass, then the forces that support them, gravity will still win, and they will collapse into a black hole. So they can be a maximum size.
Wow.
So yeah, but you definitely need these ultra energetic events in the universe to create them. And this is what we're now starting to see in detail through these gravitational waves.
So I read somewhere that a teaspoon of a neutron star weighs about 2 tons. So if you got a teaspoon and scooped up some neutron star, it'd be 2 tons. Is that about right?
I think that's far too small.
Really?
I think the number is like a teaspoon weighs about as much as humanity.
Oh my gosh!
Holy shit!
That is amazing.
Yeah. So I mean, there's a lot of interesting stuff about neutron stars. Like they have earthquakes on neutron stars. People can detect them in pulsars, etc. But a mountain on there, like Everest, would be millimeters tall. That's the biggest mountain it could create. If you could stand on a neutron star, the gravitational forces would squash you to 1 atom thick. Right? These are extreme environments, absolutely extreme environments.
That is awesome.
Yeah. That is incredible.
You got light wave or electromagnetic waves, sound waves have different frequencies and amplitudes. Do gravitational waves work that way too?
Absolutely. So the gravitational waves, so the ones we know of so far have been created by either black holes or stars spiraling together. And so you can imagine that the stars, they're spiraling around quite fast, but the rate that they spiral gives you the sort of frequency of the waves that are released. Okay. So our Earth produces gravitational waves, right? And they have a period of roughly a year, which is the orbital period, but their amplitude is really, really tiny, right? The stars that spin together, which are spinning closer and closer, approaching the speed of light, their frequency goes up such that it moves into a high frequency sort of area, and that's what we see in the detectors.
Oh, wow, okay.
Yeah.
Just how big is this detection of gravitational waves? Like, just how big is it for astronomy?
Well, it's immense, right? For an astronomer, the key thing is we have a new window on the universe. There were all these things going on in the dark, right? There were colliding black holes happening all the time, and we had no idea because they leave no visible signature. Now, with things like LIGO and on the future gravitational wave detectors, we will be able to see those events happening, right? So we have a completely new window on the universe. So it's like when you realize, you could see the universe in radio waves as well as optical light. Completely different range of things going on in the universe produce radio waves as opposed to optical light. And similarly, X-rays and gamma rays. And neutrinos is another one, of course. And now we have gravitational waves. So it's very, very exciting.
Can we really be sure it's going on? Like, there's a few things we talked about where scientists found other reasons for the signals and noise. How sure are we that these are gravitational waves we're picking up?
Pretty sure, I think. I mean, because there was such a long period where we weren't seeing anything, that gave the theorists plenty of time to work out what we should see. Now, one of the most amazing things, there's very few things that I will wake up for in the middle of the night, right? And so, international rugby is one, and an announcement of the first detection of gravitational waves is the other.
I can think of a few more that I'd wake up for, but that's for another time.
But so for me, I have seen plenty of theoretical predictions of what that wave signature should look like. It should look like a wave, and the amplitude should build, and then it goes through a very rapid thing called a ring down. That was the theoretical prediction. And when they put up the picture of the first one, I just went, yep, that's it. I mean, it was identical to what was expected. And that was the really terrifying part, that it was exactly what we expected. Okay?
Is that unusual, is it?
Yeah. Well, the fact that mathematics works and makes accurate predictions is still terrifying. Right? I mean, it's frightening.
It is. I do find it kind of weird that we can describe the world essentially in a bunch of 10 digits and a few symbols.
I know. It's incredible.
I read on your blog recently where you used mathematics to try and imagine what it'd be like kind of falling towards a black hole, and whether you kind of essentially, by looking at the mathematics, you kind of ruled out a lot of possibilities that people go on about on the internet.
Yeah. Oh, yes. Yeah. So that started because I actually had a student who was working on that kind of project, and they basically said that they'd sat around with other physicists, not just they'd looked on the web, etc. Even other physicists were trying to picture what it would look like to fall into a black hole. And you can think about this stuff, but quantum mechanics and relativity are two of those areas where intuition often goes out the window. Right? And you need to go back and say, right, let's write down some equations and see what this says. And you get the opposite answer, right, to what people sort of think. They think that you see the universe speed up. You don't. That the universe would appear blue shifted because you're in a gravitational potential. It doesn't. It looks red shifted, etc. There's all these subtleties which you wouldn't have predicted if you just had to think about it. Now and again, you've got to go back to the mathematics.
Wow, that's incredible.
Which is the cool part.
Yeah, and so you kind of look at like black holes and dark matter.
Mm-hmm.
Can you see, I know it's kind of how long's a string in my hand, but can you see some sort of future looking at gravitational waves to observe dark matter? Do you think there's a potential in that at all?
It all depends on what dark matter is. So, this is going to be the question. We know that there's dark matter. We know roughly where it is, but we don't know the details of how it's distributed. But it has an effect on how rays travel through the universe, right? So we know light rays get bent by the presence of dark matter. Okay, so you have gravitational lensing. So we can detect dark matter through that sort of process. Now we'll have gravitational waves as they travel to the universe. They too will be deflected, and how they're deflected depends on how big they are compared to how the mass is distributed. So in the future, when we can really accurately measure gravitational waves, we might have another way of seeing where dark matter is scattered across the sky based upon how much it distorts the gravitational wave signature. So people are already thinking about this. People have already calculated that the gravitational waves we saw in the last event, which had light arrive at the same time, they must have been traveling at the same speed. Okay, so at the speed of light, which is good because that's what you predict. And that the waves must have traveled through the gravitational potentials, the dark matter that it encountered, in pretty much the same way as the light did. Otherwise, you'd expect the signatures to be arriving at different times. So that already tells you something about the way dark matter is distributed. So we're thinking about it.
Oh, awesome. That's so cool.
It's a bit of a mind meld, isn't it? It's bizarre.
It is.
If there was a couple of black holes close enough and they swirling around, could we actually feel the gravitational waves, or because we're part of the space-time as well, we wouldn't be able to detect them? Or
if you were close enough, you would feel it. Because what would happen is that that gravitational effect that we were talking about, that one tube gets shorter, one gets longer, right, by a fraction of a proton. If you're much closer, then the distances that they get stretched are much larger. And put you near there, then what you would find is the equivalent of spaghettification, this thing that happens when you fall into a black hole. Your feet would be pulled one way, your head would be pulled the other, you'd be pushed in from the sides. But then
I'd be taller, though.
Yeah. But then a fraction of a second later, you'd be a lot fatter, right? Because you would get squeezed and stretched in the other direction. Human bodies aren't designed to withstand that kind of thing.
No, that's a bummer.
Yeah.
Now, Bern, you might have to sit this one out. But I was doing a calculation the other day using the Schwarzschild radius. Okay,
It's probably wrong.
That's what now, can black holes be as less dense than water? I was looking kind of like that. Doesn't that equation, Schwarzschild radius, as black holes get bigger, so the size of our solar system, like some, can they actually become they're not these incredibly dense things that we kind of see in the movies?
Well, I mean, for a classical black hole, as written down by Einstein's equations, right, there inside the event horizon is empty except for the very center. So all of that mass is located in the very center of the black hole. So most of it's got nothing in it, right? I'd have to try and do a little calculation myself. Yeah, Schwarzschild radius. It would depend on mass.
This is amazing to watch, listeners. You see Grant's just eyes rolled back into his
talking
head.
about me.
No, I'm sick of watching you.
I'd have to think about it. Yeah, there would be a mass dependency, and it would be the inverse. So let me think about it.
Cool.
I thought we were going to have a beautiful mind moment there. That was incredible. Yeah.
Oh my god, he's drawing on the walls of his house. This is weird. His wife's going to kill him.
I like to think that gravitational waves are what the Silver Surfer rides. But that's because I have no idea about gravitational waves, and I like comic books.
Well, it's an interesting question about, could you surf such a wave? Now, it does.
Yeah.
The thing is it's not quite like a water wave in that the vibrations are moving that way rather than that way. So I'm talking on a podcast.
Great radio there, right?
Yeah. Yeah, I just realised that's not going to work, is it? So anyway, I'll just put it this way: it's harder to surf on a gravitational wave, but it's not impossible because there are structures in space where you effectively take a downhill piece with you, and you're constantly sliding downhill because you take the hill with you. So
it'd be kind of falling, but forwards.
Yes.
Whoa, that's crazy.
That is pretty cool.
That's so awesome. That is so incredible.
Must be a lot of fun to play with these sort of numbers and figures and spit out what that actually means.
Well, this is one of the great things about being a cosmologist. Just a complete aside, I was in a meeting today where we were talking about how we do computer simulations of things, and there was a geologist there, and he was talking about...
You're like, boo!
No, he was good. I simulate the evolution of the Earth for 2 billion years, and 2 billion years. That's nothing.
Have a quick nap. How long's this going for? Wake me up.
Extreme environments are always interesting places.
Is that what you guys do? You kind of is it like a
You're like
battle?
a physicist clique.
Yeah,
You're like, listen to this idiot.
Geologist over here.
2 billion years, boring.
And then the quantum physicists come and go, your galaxy's staying in the same place. We've got shit going on crazy over here. Do you guys have little cliques?
We try not to. We try to play nice with
That's
them.
a yes.
They try.
That's a yes.
It was fucking quantum physicists. Oh, they're so weird. Oh, that's incredible. That is awesome. Thank you so much for joining us today. That was unbelievable.
And well done on the hat trick as well. You're the first person to agree to come on 3 times. So.
Yeah.
Is this anything to do with the fact that I live in the suburb next to you guys?
It could be. It makes it easier to find access.
No,
yeah.
you're
Camp out the front of your house. Do you agree? Yeah.
You're one of the few people that returns our emails. Okay. Professor Grant Lewis, thank you so much for joining us. You're an absolute bloody legend, and we appreciate all your time that you spend kind of looking at the universe and then communicating it. Thank you very much.
Thank you. Anytime. Number 4, anytime.
Number 4. All right, we'll hold you to that.
Okay, cool.
Thanks, Professor.
Cheers.